Welcome to the Explainer. So you've written your very first C++ program, you hit run, but what actually happens then? We're going to peel back the layers and really trace that journey from the idea in your head to a program a computer can actually understand and execute. Let's dive. Everything we're going to talk about today really boils down to this one simple, kind of funny, but powerful idea on the slide. It says, I hate this machine. It does what I tell it to do. And that's the absolute key. A computer isn't smart. It doesn't think for itself. It is an incredibly obedient servant that will do exactly what you tell it to, for better or for worse. That puts all the power and all the responsibility right on you. So, how do we actually start telling this machine what to do? Let's follow the path your code takes from the stuff you can read and write to something the machine can actually run. It's basically a two-step dance that every single C++ program has to go through. Okay, so this little sketch here lays out the whole trip. Over on the left, that's you, writing your instructions in what we call source code. You know, that file that ends in .cpp. And the goal, way over on the right, is to end up with an executable file, a program that you can just double-click and run. So what's going on in that black box in the middle? How do we get from A to B? This is where the magic happens. First, your source code gets fed to the compiler. Think of the compiler as a super strict grammar Nazi for C++. Its only job is to check if you followed all the rules of the language. Did you put a semicolon where you were supposed to? If you get the all clear, it creates this intermediate file. Then that file gets handed off to the linker, which has a totally different job to do. The linker's mission is to make your program whole. As you can see here, it takes your compiled code and then smashes it together with other pre-written code from something called a library file. You can think of this library as a dictionary that tells the computer what a command like count actually means. By grabbing those definitions, the linker builds one final self-contained executable file. We call this static linking, and it means your program has everything it needs all bundled up inside, ready to run on its own. All right, so that's the big picture journey from code to a running program. Now, let's zoom way in and look at the actual blueprint of the C++ code itself. You know, just like an essay has a certain structure, a C++ program has some fundamental parts you've absolutely got to have. So any C++ program you look at is really built from two main pieces. Up at the top, you've got these things called preprocessor directives. These are commands like #include that actually run before the compiler even gets started. They're like a warm-up act, getting the environment ready for the main event. And that main event is the program body, which always starts with int main function. That's your entry point. When you run your program, the computer jumps right there and starts executing. Now, inside that main function, you're going to be working with variables. And the source lecture had this perfect analogy for it. A variable is like reserving a spot in your kitchen for a new fridge. You have to measure the space and make sure it's the right size before the delivery truck shows up. Same thing in code. You have to declare a variable to reserve a spot in memory before you can put any data there. So how big of a spot do you need to reserve? Well, that's where data types come in. This table shows you a few of the common ones. When you make a variable, you have to tell the computer what kind of data it's going to hold. Is it a single character, a whole number, a decimal? Declaring an int for an integer tells the computer to set aside 4 bytes. But if you need a super precise decimal number, you'd use a double, which reserves 8 bytes. You're telling it exactly how much space you'll need. But what about a value that you absolutely positively do not want to change? Something like the value of pi. For that, you use a constant. You set its value once, and it's locked in. It can't be changed while the program is running. And you've got two common ways to do this, but they work very differently under the hood. On the left, using the const keyword, that actually creates a real variable in memory that just happens to be read-only. But check out the one on the right, the #define macro. This is a preprocessor trick. Before the compiler even sees your code, it goes through and does a find and replace. Everywhere it sees pi, it just swaps it out with the number 3.14. This is a clever way to save a little bit of memory and can be a tiny bit faster. Okay, so we've got places to store our data. Now it's time for the fun part, the action. How do we get information from the user? show them results on the screen, and actually do calculations. Well, C++ gives us two main tools for this: sin and count. The easiest way to remember which is to just look at the arrows. They show you the direction the data is flowing. Sin, with the double greater than arrows, takes input from the keyboard and shoves it into one of your variables. Count, with the double less than arrows, takes data from your program and sends it out to the screen. Simple as that. To actually do stuff with our data, we need operators. It's just a fancy word for a symbol that performs some kind of action. You know, in 3 plus 4, the plus sign is the operator. It's telling the computer to perform addition. And C++ gives you a whole toolbox full of them. You've got your standard mathematical ones, of course. You've got relational operators to compare things. Is this equal to that? Is it greater than? You've got logical operators to combine conditions, increment and decrement for quickly adding or subtracting one. And of course, the good old assignment operator to store a value. Now pay close attention here, because with some of these operators, timing is everything. Look at these two examples. They seem almost identical, right? But the placement of those little plus plus symbols changes everything. On the left, that's pre-increment. It increments x to 11 first and then assigns that new value to y, so they both end up as 11. But on the right, that's post-increment. It assigns the original value of x, which is 10, to y first, and then it goes back and increments x. The result, y is 10, but x is 11. A tiny difference in code, a completely different outcome. And that brings us to a really important quirk you just have to know about the assignment operator, the equal sign. It doesn't work like it does in math class. It works from right to left. The computer solves everything on the right side first, boils it down to a single value, in this case 7, and then it copies that result into the variable on the left. This right-to-left flow is what lets you do clever things like chain assignments together. And that brings us right back to the beginning. From the compiler to the linker to the order of operations, it's all a precise, logical, step-by-step process. The computer isn't being creative or smart, it is just being perfectly, flawlessly obedient. So if your program gives you the wrong answer, it's not because the computer messed up. It's because it perfectly executed your flawed instructions. And that's why we end on this question. In Arabic, it asks, code follows your words to the letter. So the question is, are your words clear? That is the entire game of programming, right there. The machine will always do exactly what you tell it. So the only real question is, are you telling it the right thing? Thanks for watching.